So let's talk about RPL protocol. This is one of the standard routing protocol that is also an important part of the Contiki operating system. And it is one of the modern routing protocols for low power wireless networks. So RPL stands for Routing Protocol for Low Power and Lossy Networks. This protocol organizes the network into one or more tree-like structures. And these tree-like structures are also called DODAG or DODAG. This stands for Directed Acyclic Graph. And the root of these tree structures is called DODAG root. And since these trees are rooted at one of the node, which is DODAG root, they are called destination-oriented directed acyclic graph. An important term to keep in mind in RPL network is the rank of the node. This defines the node's individual position with respect to the other node and the root node. In this example, depending upon the level where the node is present, it has an increasing rank from the root node. Earlier, we had mentioned that there can be multiple instances of the destination-oriented directed acyclic graph present in the network, and each of this can be routed to one of the nodes. Consequently, to identify these different tree instances, this network also has a version number field which helps it to identify different variants, and this is called DODAG ID. So to construct the routing tree, maintain its topology and update, RPL sends a number of control messages, and these are listed on the slide. So we will not go in detail about these individual messages. RPL also as a protocol supports a different flow from the root node. It can be away from the root node or it can be towards the root node. So let's now talk about wide area networks. So there are many applications where we may require much more significant range than that is offered by standards such as Bluetooth or Wi-Fi that is very commonly used on IoT devices. So we are talking about having communication at the city scale or even beyond. So let's look at some example applications. For example, the first application could be having a deployment of sensors that can help you monitor the air quality in the city. And we can talk about having it across every intersection, and we can talk about having hundreds to thousands of these sensors distributed throughout the city. So let's look at another example. Here we have an example of sensor deployed in India. And these sensors help you keep track of the traffic queue. We can typically have such sensor deployed at every traffic intersection. Here we are looking at having hundreds or thousands of such sensors again deployed across the city. And they will require to report queue information to cloud or other central device. And each of the sensor might be communicating their information over a link that spans hundreds of meters of distance. So how do we collect measurements from sensors that are deployed across the city? Should we go manually to collect these measurements? Should we connect each of these sensors to Wi-Fi or through Ethernet, or should we pay for cellular access? However, the challenge that we find is that because of the very large number of nodes that are going to be deployed in the city scale, we are talking about hundreds to thousands of or even higher IoT nodes that are dispersed across the city. And connecting through these means might just not be feasible. Why? Because it might require too much work to sort of like connect individually each node to, let's say, Ethernet or through an access point. There might also be like it could lead to many separate networks and introduce challenge on how to manage these separate networks. And if let's say we want to use cellular service, each of this node would have to pay for a certain subscription fee, and it might get too expensive because of this just the large scale of deployment of these IoT devices. So what ideally we would like is to deploy as few gateway or nodes as possible, and it allows us to have as little maintenance and scalability issue. And the network should also be low powers, and the sensors should be able to run for prolonged period of time on the same battery. Furthermore, as we don't really require very high throughput, and most of these applications only send small amount of sensor information, so that is also one of the things that we should keep in consideration. So just to give an example, sensor information such as temperature, sending temperature or humidity or pollution level might just require sending few bytes per sensor reading. So we look at some of the existing wireless standards and technology that can allow us to transmit to long distances at low data rate to enable cities scale applications. However, these, if you look at some of the existing standards, these needs are not actually easily met by any existing technology. So let's look at this in detail with the graph that is shown on the slide. So on the y-axis, we have the data throughput, and on the x-axis, we have the communication range that is achieved by the particular wireless technology. So if you look at Wi-Fi, it can achieve a reasonably reasonable range, but at a very high throughput. A Bluetooth or a Zigbee standard approaches slightly higher range than Wi-Fi, but at a lower throughput and lower power consumption when compared to the Wi-Fi radio. And typically, as we actually go lower in throughput and lower in range, the power consumption and the cost goes down. And the higher throughput that we go and higher range, the power consumption and cost goes up. So where does cellular standards lie? So the cellular standards can achieve higher range than some of the standards like Wi-Fi and Bluetooth, and they can also achieve high throughput, but then they are also higher power consuming and higher cost. So that makes them difficult to deploy on IoT devices. So what we are really looking for this city scale applications is this area where we can actually have reasonable throughput that can support these applications like sending temperature and pollution monitoring, and at high enough range and at reasonable cost and power consumption. And this need has not been met by some of the traditional protocols that have been deployed over the last 2 decades. And that actually led to the development of these low power wide area networks and protocols that we are going to talk about. So what would be the physical characteristics of wireless standards that can support this capability? And how would you design a physical layer for these wireless standards? So let's look at specific parameters such as modulation, transmit power, carrier frequency, throughput, and bandwidth. So we would ideally want to keep the modulation scheme to be simple enough so that it can operate on devices that are operating on simple batteries. We would also want to keep the transmit power to be not as high as possible. Uh, we would want to keep the transfer power to be reasonably high that you can get sufficient range, but it is not high enough that it just drains out the battery. We would also want to use lower frequency as it has better propagation characteristics. That means that you can reach as high range as possible for the same transmit power. Similarly, we would want to keep the throughput to be low, as we will see that the receive sensitivity improves as we lower the throughput and bandwidth. Similarly, as we are sending small amount of information, like the sensor information that we talked about, it would also require low data rate and low channel bandwidth. So all of these are like important design choices to keep in mind for designing file layer for these long range low power protocols. So let's just go back and look at an example of a system that I worked on for my doctoral work. And this was a system called Loria, and it was presented at ACM Census in 2017. And it allowed wireless transmission at only 70 microwatts of power consumption at the transmitter device. And more importantly, it was able to achieve a very high communication range, in fact, even at the order of kilometers in certain settings. So one of the important ideas that we had incorporated in the design of the system was that the receive sensitivity improves quite significantly as we transmit at lower bit rate and thus the bandwidth. And in case of Loria, as we show on the slide, we used a bandwidth of tens of kilohertz, and it allowed us to support very high receive sensitivity. And what we found was that this was not very detrimental to many sensing applications, as most sensing applications, as we talked about, only send small amount of information. So at the end, we were transmitting at a data rate of 1 kilobits per second using 2FSK as a modulation scheme, and it allowed us to achieve a receive sensitivity of about minus 124 dBm. And this is a great example of trade-offs between receive sensitivity, range, and bandwidth. And such trade-offs are applicable to most wireless systems. As a designer, you are often tasked with trying to balance these trade-offs to enable maximum range and support the needs of the application while keeping the power consumption to be as low as possible. So next, let's look at how should be the medium access control mechanism for designing such low power, long range wide area networks. Typically, we are looking at a star kind of topology where there is a high power gateway device that can be externally powered, and a number of battery powered or even battery free devices, which are the end devices which are communicating to this gateway device at the center of the star topology. Hence, there is typical asymmetry in the computational and device capabilities that is present within the network. And secondly, that we should have all these end devices to be off for most of the duration of time. And the reason is that it allows them to conserve their battery. And due to the weak links, long range, and heavily duty cycle end devices, any sort of synchronization protocol or mechanism should be avoided, because it might be difficult for you to synchronize these large number of simple devices that are communicating over long distances. Hence, mechanisms such as TDMA is also out of question. So typically under all these constraints, TDMA is definitely not the most appropriate. So we also can rule out CSMA because of a set of reasons. And typically for these networks, Aloha kind of simple medium access control protocol is commonly used. So typically we can summarize some of our learnings from this lecture is that some of the main qualities for LPWANs are they can operate at unlicensed frequency band, they transmit a reasonably high transmit power, they have low data rate, which is typically 100 kbps, but much lesser in most deployments. They support range of hundreds of meters to kilometers, and they have simple access and control mechanisms without any synchronization. For example, mechanisms such as Aloha. So in the next part of the lecture, we look at specific instance of these characteristics put in action for supporting two widely used low power wide area protocols such as LoRa and Sigfox. Thank you.